Hi, welcome to Technical and Engineering Academy. This is Blessed Elvis. Okay, so there is a theorem that is used before we start answering the questions. There is a formula that is used. Now, instead of diving direct into the formula, let's derive it. So let's say we have been given the power of series where we have, let's say, f of x equals to, let's say, a0 added to a1 x added to a2 x squared added to a3 x cubic added to a4 x power 4. It will just keep on increasing just like that when you just keep on adding. So let's say we have this as our series. So in this case then, for us to derive the formula used for MACLAURIN, in this case then we are going to say, let where there is x we put 0 at first. So firstly, where there is x we say let there be 0. So what are we going to have? We are going to have f of 0 equal to a0 added to a1 0 added to a2 0 squared added to a3 0 cubic, and it will just keep on going like that. Now our main interest here will be here because this and going all over, the x values will be cancelled. So we are just going to remain with f of o equal to what? Equal to a0. So let's keep this. So make sure that you keep it somewhere because this is going to help us. So whenever there will be ao, we are going to replace with what? With the f of o. So since we are done with this part, let's also try to derive or to differentiate. Let's differentiate with respect to x. So finding the first derivative, remember our first expression of f of x is what? a0 plus a1x plus, let's say, a2x squared added to a3x cubic added to a4x power 4 x power 4, and you keep on going. You can even end up to the fifth power of x, or rather where the value of x is unknown. Okay, so in this case then, let's differentiate this series that we have. So when we differentiate ao, what are we going to have? Of course, we are just going to have 0 plus, what's the differentiator of a1x? It's just a1. Differentiating a2x squared according to power rule, this power 2 to x will drop down, and then we are going to have a2 then x here. Same applies to this one. The power here will drop down. We are going to have 3 x, then the power will reduce by 1, so we are going to have 2 added to, then a4, sorry, this is a, okay, this is a, so a4 x4, the 4 will drop down. We are going to have then what? We are going to have a4, let's just write that properly, a4, and then x will drop by 1. We are going to have power 3, and we should just keep on going like that. So in this case then, the first derivative will be x equals to a1 added to a2 x added to 3 x squared added to 4 x power 3. So we are just ending on power 3. You can keep on going just like that. So in this case, the main point here is to derive the MACLAURIN's theorem. So in this case, let's say where there is x, we put 0. So let's just create space so that we can see what will happen next here. Okay, so remember we are first deriving the formula instead of just going direct into the formula. let's know how this is coming about. So when you replace where there is x with 0, what are we going to have? So in the first derivative, we replace with 0, we are going to have a1 plus. Now in these, when you replace with 0 in these are going to cancel out, because 0 multiplied by, let's say, 2a2, it's just 0. 0 multiplied by 3a3, it's just 0. 0 multiplied by 4a4, it's just 0. So in this case, when we add here, when we add where there is x with 0, of course these are going to be cancelled. So in this case then, we are just going to remain with what? Only a1. So in this case, our first derivative, when we replace with 0, we are going to have what? a1. So let's keep that also. So remember, we have two things. Firstly, when we replaced with 0 here, we had what? We had a 0. When we replaced with what? With the first derivative here, we had what? We had a 1. So let's replace also, let's differentiate twice as well. So let's differentiate twice. So the first derivative, remember, the first derivative was equal to, the first derivative was a1 added to 2a 2x added to 3a 3x squared added to 4a 4. So that, make sure that you are just getting what I'm saying. Sometimes the handwriting might be bad. So we have 3 here. Okay, so in this case, this was our first derivative. So let's find the second derivative. So the second derivative of this will be what? So the second derivative of this is going to be, so this is going to be 0 since we don't have x. Then this one is going to just remain what? 2a 2 added to, this is going to remain with, so when we multiply this 2 power here with 3, we are going to have what? 6a 3x squared, the power, or rather the x, because the power will drop by 1 and we have x squared there, so we are just going to have x. So in this case again, when you multiply 3 here with 4 here, we are going to have what? We're going to have 12a4, then x power what? 3. Okay, so this is how it's going to be. Now even on this one, we also let x equals to 0. So when you let x equals to 0 and then we replace where there are x values in here, what are we going to have? So in this case then, our second derivative will be what? 0 will be, so in this case here we don't have any x value, so we are just going to have what? 2a 2. We are not going to replace. Then in here, when we replace where there is where there is x with 0, 0 here, when you multiply 0 with these values, it's going to be 0, so we can cancel out. And then even here, when you replace where there is x with 0 and then multiply with 2a4, or 12 rather, 12a4, it's going to cancel out. So in this case, we are just going to remain with what? 2a2. Okay, so let's just create space on top here since there are a lot of things here. Okay, so I hope that you can see the pattern that is being developed here, and make sure that you are taking note of the values that we are having. Remember, at first we had what? FO equal to what? Equal to AO. Hopefully you are writing somewhere. Equal to AO. Also we had the first derivative value of 0 equal to what? A1. So this time we are looking for the second derivative. So the second derivative, let me just cancel this, it was supposed to be the first derivative. So the second derivative, when we replace where there is x with 0, we are just going to have what? 2a2. So if you can see the pattern, we had a1, a0. So let's just make a2 the subject here. So we have the second derivative of 0 equal to a2, a2. So let's make a2 the subject so that we can have a pattern in such a way that here we just have the values of a's. So this and that will cancel. So we're just going to have, okay, let's remove this down here since we don't need it anymore. Okay, so in this case then we are just going to have second derivative of 0 divided by 2 equal to what? A2. So this is our second derivative. Okay, let's keep on going. Let's also end up to maybe fifth. So in this case then, our second derivative was, we also have to find the third derivative, fourth derivative, up to fifth derivative. You can even go ahead of that. So it doesn't matter where you end. What is important here is noticing the pattern that we are developing, okay? The pattern that we are having. So in this case, our second derivative was what? 2a 2 plus 6a 3x plus 12a 4x squared plus, so if we added for the fifth one, what could be the value? Of course it could be 20. If you just follow up what we have been doing and then you add the value of 5, then we could have had 20 a5 x power 4. So that could have been the case then, or x to the power 3 rather. Okay, now let's just end up to x power 2. Okay, so let's find the third derivative from here. So the third derivative, of course, is going to be x here equal to, this one is just going to be 0, and then when we differentiate this one, it's going to be what? It's just going to be 6a3, because x will just go out, and then when we differentiate this, 12 multiplied by x power 2, of course we are going to have 24. So 24a4, then x. So let's just end up to here, up to this series. So in this case, when we replace where there is x equal to 0, what do you think could be the third derivative when we replace with 0x? So in this case, here we don't have any x value, so it's just going to be 6a3. Then here, when you replace where there is x here with a 0, this 0 multiplied by 24 is just 0, so this is just nothing. So it's going to be just 6a3. So now let's also, like we did previously, make a3 the subject of the formula. So we are finding the values of a's in this case. Okay, so let's replace where there is x, or rather let's make a3 the subject. So in this case we are going to divide 6 throughout. So we are going to have the third derivative of 0 divided by 6 equal to what? Equal to 6a power 3 over, or rather it's not power there, it's down here, so over 6. So this and that will cancel. So in this case we are going to have a3 equals to the third derivative. So make sure that you are taking note of the pattern that's being formed in here. Okay, so this is what we have as our a3. Okay, so in this case we have our a3. Now where we have 6, of course this is the same as 3 factorial. When you find the value of 3 factorial in calculator, it's going to give you 6. So instead of writing 6, of course we can as well write to say a3. That is just to shorten the process anyway, but there is no harm if you just leave it like that. It's just okay. If you are not comfortable with this, it's just okay to leave it like that. So this is our a3. Now if we keep on going, we are going to find the pattern such that a4 is going to be what? Fourth derivative of 0 of 4 factorial. Even for fifth, we are going to have fifth derivative of 0 is going to be 5 factorial. Even if we found the sixth, of course it's going to be 6 factorial. So what the pattern is that the value you have here is the factorial of the value you are going to have here. As you might have noticed, even here, the value that you have here is the pattern that's going to be formed here. So in this case then, we have our a0 equal to, let's just arrange the values together. Our a0 was equal to fo, our a1 was equal to first derivative of o. Okay, our second value of a was equal to, so since there is a 2 here, it means on the denominator you are going to have what? Okay, we are going to have 2 factorial Now you will notice that at first I didn't put factorial, so 2 factorial or just 2, it's just the same value. So when you have 2 factorial, it's just 2, or when you just have 2, it's just 2. Then our a3 was the third derivative of 0 over, since we have 3 here, we're going to have what? 3 factorial. And then if we go as further as finding the fourth, of course we're going to have fourth derivative of 0 equal to 4 factorial. Even if we went as further as finding the fifth value, we are going to have fifth derivative of 0 having down there the fifth factorial. So this is a pattern that is being formed. Now remember, at first we had f of x as our powers of series, which was a0 added to a1 x added to what? a2 x squared added to what? a3 x power 3 added to what? a4 x power x power 4. Sorry, there it just has to be power 4. Okay, power 4. Okay, let's just remove that. So in this case, then we are gonna have power 4 here for x. So that's how it is. Now remember, we have found these values, the values of a's. We have found them. So it's just to replace them where there are these values with what we had already found. So if you have taken note of that, f of x then will become, what was our AO? Our AO was f of o. Okay, then our a1 was the first derivative. Okay, then our a2 was what? Our a2 was the second derivative, 0 of 2 factorial. Then our a3 was what? Our a3 was the third derivative of 0 over 3 factorial. So you can keep on adding just like that. Our a4 was what? Our a4 was, so let's just add it from here for the sake of space. I hope that you are taking note of that. So we are going to have the fourth derivative of o over 4 factorial. If we go up to fifth, then it's going to be fifth of o, fifth derivative of o. Here we are going to have fifth factorial. So in short, to keep this short, let's just say, let me just write this as shortly as I can so that we might see. So here I've just replaced where there are a values with what we had found. So in this case, our MACLAURIN's theorem becomes f of x equals to f of o added to the first derivative of o x plus the second derivative of o over 2 factorial plus the third derivative. Now you can keep on going, and then the value is gonna, the pattern is just gonna be the same like we have done before. So this is how we find, or we derive, the formula for the MACLAURIN's theorem. So this is the formula that we are going to be using throughout the given questions. So when you have been given an expression, let's say a function, what you have to do is replace where there are x values with a 0, and also find the derivatives. So in the given expression, first you replace with a 0, you take note of the value, you derive the given function, you also replace with a 0, you take note of the value, you derive for the second time, you replace with a 0, you take note of the value, you also replace the third time, you also replace where there is x with a 0, you take note of the value. Oh, yeah, that's how you keep on going. Sorry, I forgot to write the x values here. There should be x values here. Okay, so sorry about that. Okay, so make sure that you take note of that one. Okay, so in this case, we are supposed to have the second derivative here of 0 x squared. Okay, so x squared over 2 factorial added to, if you want you can say 3x power 3 factorial of the third derivative, okay, of the third derivative, like I had written in the first place. So this is the theorem we are going to be using. So let's just look at a few examples. Okay, so in this case, let's say we have been given the series. Let's say we have been given the series to say, let's say determine the first 4 terms of the power series for, let's say we have been given a function where we say f of x equals to cos x. So the first thing that we have to do for us to find the terms, the first 4 terms of this, let's find the expression or the other function where x equals to 0. So when you replace where there is x with 0, what are you going to have? You're going to have cos x of 0. So what is cos x of 0? So cos of x, cos of 0, of course, it's going to be 1. So you can just take note of that on your calculator. So where there is cos of 0, it's just 1. So we have found the value of f of o. So according to the series that we had, or the theorem, we have to find also the derivatives. So let's take the first derivative of the given function. Remember, the given function is cos of x, and also make sure that you are taking note of the values. So cos of 0 has given us 1. So let's also find the first derivative. So the first derivative of this, what is the derivative of cos, is negative sine x. So in this case, let's also replace where there is x with a 0. So what are we going to have? So the first derivative we replace with a 0. We are going to have, what is the sign of 0? It's just 0. So in this case, we have 0. So where there is, okay, instead of writing cos o, let me just write f of 0 has given us 1. Then the first derivative has given us what? 0. Okay, so the first derivative, remember, was what? The first derivative of x was negative sine of x. So what's the second derivative of this? So let's find the second derivative. So the second derivative of negative sine is negative cos x. So in this case, let's also replace where there is x with a 0. So we are going to have the second derivative of 0 is going to be negative cos of 0. So remember, the derivative of cos is 1. So if we have a negative here, we are going to multiply negative multiplied by positive 1. So we are going to have negative 1. So in this case then, the derivative of the second derivative of 0 is giving us negative 1. So make sure that you are taking note of these values. So let's also find the third derivative. Okay, so let's just wrap this part here, since we don't need it anymore. So in this case then, remember that the second derivative we had of x was negative cos of x. So what is the third derivative of negative cos of x? Well, the second derivative of negative cos of x is sine x. So in this case then, we are going to replace where there is x with a 0. Okay, we are going to have the third derivative of 0 equal to sine of 0. So what is sine of 0? Okay, of course we have discussed that already. Sine of 0 is 0. So in this case then, our third value of 0 for this third derivative is giving us 0. Okay, so let's just create space here. So let's just go up to the sixth derivative. So you may go ahead and do that before we find the values here, so that you will assess your understanding with what we have done here. Okay, so in this case, our third derivative of xc was sine x. So let's find the fourth derivative of this. So the fourth derivative is equal to, what is the derivative of sine x is just cos x. So when you replace where there is x with 0, we are going to have the fourth derivative of 0 equal to cos of 0. So what is cos of 0? It's just 1. So where there is fourth derivative here, we are going to replace with 1. Okay, so let's also create space again. So you can also find the fifth derivative before I do. So these are the values that we are going to replace in the theorem. So where there are functions for these derivatives, we are going to replace with the values that we have found. Okay, so in this case then, let's find the fifth derivative. So remember our fourth derivative of x was cos x. So what is the derivative of cos x? Okay, so for the fifth derivative, let me just okay, for the fifth derivative, the derivative of course we know it's negative sign. So when we replace where there is x with 0, we are going to have the fifth derivative of 0 equated to negative sine of 0. So what's the derivative of sine? Is just 0. So even if we have negative there, it's just going to be 0. So in this case then, our fifth derivative is gonna of 0, of course. Our fifth derivative of 0, let's just write it here for the sake of space. Our fifth derivative of 0 is gonna be 0. Okay, so let's replace also, or rather let's first wrap this before we replace. Why am I going to up to the sixth derivative? Remember, we have been told that we should have 4 terms in this expression. Now when you replace where there are these derivatives with 0, we are going to have 0, so we are not going to have 4 terms. So in this case, we only have the values that are going to give us the terms as being 1, 2 here, and 3. So we have to make sure that we have 4 terms, since these are going to give us 0. Okay, so let's go up to 6th term. If it's going to give us a value, if no, it's not going to give us 0, then we are going to end up to that point, because we have been told to write only 4 series or 4 terms. So in this case then, remember we had our fifth derivative of x equal to negative sine x. So in this case, what is the sixth derivative of x of this? So the derivative of sine is just cos, so here we're going to have negative cos of x. So if we replace where there is x with 0, we are going to have the sixth derivative of 0 equated to negative cos. So where there is x here, we are going to replace with what? With 0. So what's the derivative of cos? It's just 1. So multiplied by negative here, we are going to have negative 1. So in this case, it implies that our sixth derivative is also negative 1, which is giving a definite value instead of 0. So in this case then, our sixth derivative of 0 is giving us negative 1. Okay, let me just, negative 1. Okay, so these are the values that we are going to replace in the theorem. So make sure that you write these values somewhere, because I'm going to remove them for the sake of space. Okay, so let me just do that. So remember that the theorem was f of 0 plus the first derivative, where there is x, we put 0, plus the second derivative of 2 prime of what? Of f 0 plus the third prime of the third derivative of not x 0 0 plus, since we have gone as far as the sixth, so let's go as far as that. So even x power 4, okay, and then fourth, then here we have the derivative of the fourth of 0 plus we have x 5 over 5 factorial, where there is the derivative of f of 0, the fifth derivative rather. So we also go up to the sixth, where we have the sixth factorial, and then we replace where there is also the sixth derivative of 0. So let's replace now those values that we had. So if you recall, if you have taken note of the values that we had, okay, so in this case then, where we have f of o, remember our f of o gave us what? 1. So we're going to have 1 here. And then our first derivative gave us what? 0. So 0 here, we are just going to have 0 here. So it's just going to be 0 added to x squared over second factorial. In this case then, the second derivative gave us what? So the second derivative gave us negative 1. So we are going to have negative 1 in the brackets there, then added to 3x over 3 factorial in this case. Then the third derivative gave us what? 0, so it's going to be 0 here. Okay, and then we add it to the fourth. Okay, so 4 over 4 factorial. Then, okay, let me just wrap this for the sake of space and also avoid being confused. So I'm just going to remove this. So of course I'm sure that you have followed up to this far. So where there is the derivative of the fourth one, we had what? We had 1. So we are going to have 1 here, and then added to, so here there is 4. Make sure that you take note of that. And then here there is 2. So in this case, the fifth derivative, so fifth factorial, so the fifth derivative gave us what? Gave us 0. So in this case, it's going to be 0 here. And then the sixth, so let me just add it here. So the sixth is going to be x power 6, sorry, power 6 over 6th factorial. So in this case, our sixth derivative gave us what? Negative 1. So let's simplify now the expression we have. So in this case, we are going to have f of x equal to, so here we have 1, and then here we have 0, so we just have to omit that. Then positive multiplied by negative, we are going to have negative x squared over 2 factorial. Then here 0 multiplied by x power 3 over 3 factorial is just 0, so we are going to have 0 there, so we just cancel that. Then here 1 multiplied by x power 4 over 4 factorial is just x power 4 over 4 factorial. Okay, so also here when we multiply this 0 with x power 5 over a fifth factorial, it's just 0, so we just have to ignore that. Then we come here where we have positive and negative. Here we are going to have negative. Then 1 multiplied by x power 6, we are going to have x power 6 over the 6th factorial. So the c's, we just keep on going just like that. So let's simplify further. Let's work out the factorials that we have down there on the denominators of the values. Okay, so in this case then, alright, let's remove that. So in this case then, we are going to have the function f of x equal to 1 minus x squared over, what is the second factorial? When you write 2 factorial on your calculator, you're going to have 2. So the factorial here simply means you are multiplying with the less values up to 1. What I mean is, let's say where we have 2 factorial, this is the same as 2 multiplied by 1. Where we have third factorial, it's the same as 3 multiplied by 2 multiplied by 1. Where you have fourth factorial, it's the same as, okay, rather let me just write factorial. Where you have factorial, it's the same as 4 multiplied by 3 multiplied by 2 multiplied by 1. So make sure you take note of that pattern. So when we say 2 factorial gives 2, it means when you multiply 2 multiplied by 1, we are going to have what? We are going to have 2, of course. So that's how it is if you don't, in case you are not using the calculator. So that's how we go about it. So 2 factorial is just 2. Then what is 4 factorial? So 4 factorial in this case means 4 multiplied by 3 multiplied by 2 multiplied by 1, which of course 4 multiplied by 3 is 12, then 12 multiplied by 2 is 24, then 24 multiplied by 1 is what? It's just 24. So in that case then our 4th factorial is 24, so we're going to have 24 down there. Okay, so let me just remove this here since it's not necessary. Then what about when you have the 6th factorial? So the 6th factorial in this case is gonna mean 6 factorial equal to 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So when you multiply all these values, you are going to find out that when you multiply these values, you are going to have 720. So in this case, it's going to be 720. Okay, so let's replace that. So where there is 6th factorial, we are going to replace with 720. So these are the values of the factorials we have. So that's the pattern behind. So in this case then, this series can keep on going just like that. So this is the answer to the question. So in this case, where there is cos of x, this first 4 terms we are going to have are 1 subtract x squared divided by 2 added to x to the 4th power over 24 subtract by x to the 6th power over 720. So the series can keep on going like that. So that's the answer. So now that's how we go about this. So let's say you had where taking note of what we have, the values we have. Let's say they said the series where where we have cos of 2 theta. So how can you go about this one? So the procedure is the same. So remember, after we had found, if you have been given this, or rather let me just write the function. If you have been given cos of 2 theta, in this case you can represent to say let x equal to 2 theta, then you do whatever we have been doing before. After you have found the series, you replace now where there is x with 2 theta. So if you have been given a function where they say cos of 2 theta, remember our function for f of, or rather let me just use cos. Our function for cos of x was what? Was 1 minus subtracted by x squared divided by 2 added to x, rather let me write this properly, added to x to the 4th power over 24 subtracted to subtract x to the 6th power over 720. Okay, 720. Okay, let me just write that properly. Okay, 720. So this was our cos of x. Now, when we replace where there is x with 2 theta, what are we going to have? So we are going to have cos of 2 theta. I am used to writing. So where there is x, of course, we say there is 2 theta. So here it's squared over 2. Then added to 2 theta to the 4th power over 24. Subtract 2 theta to the 6th power over what? Over 720. Okay, so let me just create space on top here. So hopefully you are following. I've just replaced where there is x with 2 theta since we have already done the cos of x. So let's simplify that. So cos of 2 theta, it's gonna be 1 subtract. So here there is squared. Now 2 raised to the 2nd power, it's what? It's 4. So it's gonna be 2 theta. Then also theta squared is just squared here over 24. Okay, and then added to 2 to the 4th power is what? Is 16. So we're going to have 16 theta to the 4th power over in this case over 24. So here we had 2. Sorry, I had forgotten. Here it's just 2. It's not 24. So 24 has to be here. And then here we have to have 2 here. Okay, and then subtract. Then 2 to the 6th power. Here it's 6. So 2 to the 6th power we have 64. Theta of the 6th, theta 6 power 6 over 720. So these are the values that you have here. So let's just create space down there now, since we have already used this. So in this case then, we are gonna have, so let's simplify this. So cos of 2 theta is gonna be 1 minus 2 into 4 is what? It's just 2. So theta squared, then plus, now 16 over 64 over 24 rather. When you simplify that, you are going to have 2 over 3. That is, when you divide 8 into 16, it's 2. 8 into 64, or rather 24, it's 3. So then theta raised to the 4th power minus, then you also divide where there is 64 over 720, you also replace the values there. So when you say 16 into 64, that is 4 over 16 into 720, it's 45. So 45 theta to the 6th power. So this is the value where, in case you have been given cos of 2 theta. So that's all about this. So remember, always you should remember the theorem. So the theorem is what will guide you into finding the values. So remember, our theorem was this, and then it was followed by what? It was followed by the first derivative of 0x, followed by what? The x squared over 2 factorial of what? Of the second derivative, followed by what? Followed by x power 3 over third factorial of the third derivative of 0, followed by x to the 4th over 4th factorial of the 4th derivative of 0. The function can keep on going just like that. So this is the main function, or rather the main theorem that you should be able to remember. So whatever question you have been given, you first have to replace where there is x, or rather where there is a certain given variable with 0, and then you find the first derivative and then replace with 0. You find the second derivative and then replace with 0. You find the third derivative up to whatever the number of terms you have been given. After you have done that, then you start replacing where there are these values. So where there is this value, replace with according to the value that it gave you, and then you replace in this theorem. Then that's your answer. So whatever value you have been given, you just do likewise. However, there are certain conditions where the MACLAURIN's series does not work. The first one is where you have a function that does not give the exact value, where, let's say, this is the first theorem, or rather the first condition. If the function gives you, let's say, after you replace the function, then it gives you the infinity, then value, then the MACLAURIN's series does not exist there. So the function f of o should not be equal to the infinity value. Let's give an example. If you have, let's say, f of x, let's say you have cos of x. So if we replace where there is x with 0 in this case, we are going to have what? F of 0 equal to x cos of 0. So in this case, what is cos of 0 is just 1. So since this is given a specific value, then you can proceed to finding the what? The MACLAURIN series. Now, if you have, let's say, a function f of x equal to ln of x, when you replace where there is x with 0 in this expression, you replace where there is x with 0, you are going to have what? You are going to have negative infinity. So since this value is given infinity, it means that the MACLAURIN series does not exist because this does not meet the condition. Hence, you cannot proceed to find the series for the MACLAURIN according to his theorem. So in this case then, you are not going to proceed. So after you have been given the function, it's very much wise that at first you replace where there is x with 0. After you replace where there is a variable, whatever variable is present, it's not always x, you replace and then it gives you a specific value. Then you can proceed to finding, or rather to replace where there are values of the derivatives with 0. But after you replace and then you find that it's giving you infinity or negative infinity, then you just have to stop right there. You just have to say the MACLAURIN's series does not meet the condition, hence it does not exist. So that's how it is, because for where we have this function here, sorry for that, where you have this function here, ln of x, when you keep on deriving this, still you are just going to be having the what? The infinity value. So hence it does not exist. Okay, that's how it is. So again, the other one is that the second condition where MACLAURIN's theorem or series does not exist is where you find out that the derivatives, let's say the first derivative, the second derivative, and let's say the third derivative, whatever number of derivatives you might have, if they are giving you infinite also, the first one we had talked about is where you just replace in the function that you have been given, you just replace with x, and then after you replace with the 0 value, it gives you infinity or negative infinity, then it does not exist. But for this one that we are about to talk about is where you have been given the derivatives. Okay, after you have found the derivatives, in the first one it can exist, and then in the given derivatives you find that it does not exist, it gives you an infinity value. In that case, then this does not meet the MACLAURIN's principle or the theorem, hence the MACLAURIN's series does not exist. Okay, let me give an example. Let's say you have f of x, the one that we had, cos of x, and then when you find the first derivative of this, it's gonna give you what? Okay, it's gonna give you negative of sine of x. Then you replace where there is x with 0. What are we going to have? So the first derivative in this case is gonna be 0. Okay, so this one is meeting the condition because we have the value. Okay, now let's say you have f of x equal to ln of x, and then you find the first derivative. So what's the first derivative of ln of x? The first derivative of ln of x is 1 over x. So when you replace where there is this value, rather it's not that, the first derivative of this, rather, so when you replace where there is, it's ln of x rather. So when you replace where there is x with 0, you are going to have 1 over infinity, or rather 1 over 0. Okay, the first derivative of ln of x is 1 over x. So in this case, when you replace where there is x with 0, what are you going to have? Of course, this on the calculator is even going to specify to say it does not exist, so, or rather math error. So in this case, it's just infinity. So 1 over 0 is infinity. So in this case, it does not exist. So we have seen that after we have found the first derivative of ln of x, and then we replace where there is x with 0, it's giving us infinity. So in this case, then the Maclaurin series does not exist, because according to the conditions, the derivatives shouldn't give you what? Shouldn't give you the infinity. So that's how it is. So this is the second condition. There are 3 of them. So the third condition says that the resultant Maclaurin series must be convergent. Okay, what does this mean? This means that the values of terms, or the group of terms that you have, must act progressively. Okay, must get progressively smaller, and the sum of the terms should of course reach a limiting value. So where you have been given the number of series, the values, when you are adding them, they should be adding progressively. What this means is that you can be given the number of series, and then when you keep on adding, they give you a very small number. When you keep on adding, then the Maclaurin series there exists. Okay, so let's say you have been given 1 over 1 over 2. So this is our series. Let's say 1 over 4, then added to 1 over 8 plus. Okay, we keep on going just like that. So in this case, this is a convergent, since the value of the terms is getting smaller, and the sum of the terms is approaching a limiting value of what? Of 2. So when you add these values, you are going to find that it's adding progressively. Okay, so let's add these values. Let's say 1 added to 1 over 5, 1 over 2, added to 1 over 4, added to, so in this case we are ending up to what? We are ending up to 8, 1 over 8, so adding up to 1/8. So in this case, it's giving us 1.875. So this is where we are ending when we add this value. So if you keep on adding, let's say 1 over 16, you keep on adding 1 over 32, you keep on adding, you find that with progress, for it to reach at this point, it will take a very long time for you to keep on adding them. So in this case, this is approaching the value of 2 progressively. So this implies that this series meets the Maclaurin series. Thanks once again, guys, for staying this far. Please like, subscribe, share, and turn on the notification button so that you are updated whenever I upload a new video. Stay blessed.